Hello everybody, how are you? Good to see you again. Happy Friday. I guess it's time for the Putnam class. I'm just going to put everyone here. Quick check. I want to do a quick sound check. Are you guys able to hear what I'm saying? If you can maybe, yep, I see the thumbs up. That's good. I can also see the chat that's going on. I will say this is actually streaming on YouTube right now as well, but don't worry, nobody in the actual class is streaming on it. I'm just streaming my video feed because people from other universities, I think, were a little bit curious what we do in this Putnam seminar. And as they'll soon see, we just do interesting questions. So today I want to talk about polynomials. But before doing that, I want to mention something. There was a homework that was due. Please do submit that on the Canvas at some point. We'll, I guess, grade it at some point. Just the only reason we say do it soon is because you don't want the homeworks to pile up on you. And something else I also want to really encourage is that the homeworks were designed for people to work together. They're not much fun to work. Well, actually, that's not true. They're a lot of fun to think about on your own too. But half of the purpose of this class was to get people to get to know each other. So I strongly encourage you to use the CMU Discord or other services to go and get a group of people to think about the questions together. Okay, but today we want to talk about polynomials. What's up with polynomials? Actually, before I pull out the questions for today, I just want to say, what's the point of polynomials? Well, in some sense, polynomials are just a way of describing functions with ever greater ideas of complexity. I mean, in some sense, what's the simplest function? Okay, we're going to do the same thing as usual. If you have something you want to say, just type raise hand into the chat and I'll call on you. That way we can have people's voices, which is more fun. What's the simplest type of function, if I'm talking about functions in the world? Raise hand. So I got something from Jack Parkhouse. What do you have?
Y equals x.
Y equals x. Wow. You're a pretty sophisticated person. You already got to y equals x. I'm going to put some simpler ones first, and then we'll get to y equals x. I have a very simple one. It's called f of x equals 0. This is my simplest function. Somehow the next simplest function, I'm going to get a little bit more fancy. F of x equals a constant, like 5. And then next, I'll get a function which is f of x equals x. Now, can anyone say what's the notion of the complexity here? I do see there's another hand that had raised. Sana? Is it Sana Imani?
Yeah, I mean, basically you're saying that whatever for the constant one, you're saying whatever the value of x, you're still gonna get 5, right? And then for the f of x equals to x, x and y are always going to be the same.
Yeah, so there's some notion of like somehow the previous ones, like 0 and 5, there's really nothing going on. It's always going to be the same. It's constant no matter what x you put in. And then suddenly here, there's some linear type relationship. That's what's going on. But what I'm trying to say is these are like the different varieties of functions. And before I go to other ideas, I'll say even this is useful. The idea of a linear function is useful because if anyone ever gave you the function e to the x, random tip, if you're ever drawing e to the x, draw the e to the x first and then draw the axes. That's the best way. If you draw the axes first and then draw the e to the x, it's a disaster. But somehow the reason I did this is because now I can also have the tangent line, right? Because it turns out that e to the power x, let's do a better job, e to the power x has a tangency line, which is x plus 1. And that in fact, that linear approximation to e to the x is one of the most useful approximations in all of mathematics, e to the power x being approximately equal to x plus 1, or 1 plus x. But the notion is that somehow these are ideas of simple functions, and as you get more and more complex, that's when you get to polynomials. Polynomials are just like, well, the next degree up that happens to be quadratic. So anyway, that's the idea of polynomials. And now let's start doing some questions about polynomials. So I'm going to pull over to the questions for today. This I'm just scrolling down on the course website, Polynomials lecture. What do we have today? Okay, so I want to start with the first problem on this sheet. So if you want to follow along, the place that you can get this particular handout is this is just the course website, and I happen to click on this year's Putnam course, and then I clicked on the polynomials. And I want to talk about the problem number 1. That is, let's do this. Section 2, problem number 1. We're supposed to show that some real polynomial, the sum of ai x to the power i's, has at least one real root if the sum of the ai's over I plus 1 happens to be 0. I'm just going to copy the gist of that question onto the blackboard I'm using. And so what I have is I've got some real polynomial. I'm supposed to show that there's at least one real root. Just a second. So the question is, you want to show that this real polynomial sum of, not n, I equals 0 to n, ai x to the I has at least one real root. A's are real numbers. Real root if the sum from I equals 0 to n of ai over I plus 1 equals 0. Does anyone have any ideas of how to start on this kind of a question? I don't want a solution. If you've seen it before, don't give it away. That's no fun. But if you have even a little idea that somebody else can jump off of, I'm curious. Oh, I see there's a hand up. So idea is the same as raise hand. Adavate Nene.
Alright, so AI over I plus 1 looks a lot like we just put the integral of the polynomial.
Okay. This could be useful somehow. ai over I plus 1 looks suspiciously. Say again?
And then like plugging in 1.
And plugging in 1. It's like it's an integral where you're plugging in x equals to 1. This is a great idea. And indeed, when you try to solve questions, you start with these kinds of vague ideas. See if they jog other people's ideas. Who else wants to add? I'm watching for these raise hand or ideas in the chat. And I don't expect you to solve the question right away. It should be something where we have a bunch of ideas. Ooh, here comes something. Raise hand. Alex Cui. Are you saying that it's equivalently, you want to assume there's no real roots and then find a contradiction? Is that what you mean?
Yes.
Yes, okay. Equivalently, assume no real roots and find a contradiction. So either of those techniques, well, I mean, this second technique would give you a proof. You would be done. It's just that you need to somehow find that contradiction. And then this idea is like, maybe we can do something with this. I see there's more ideas. So, Subhasish. You'll have to speak up a little bit, remember. You got to get closer.
Just to finish the thought in 1, I'm pretty sure it's the integral from 0 to 1.
Oh, you're saying if I just integrated from 0 to 1 of a particular polynomial, actually the polynomial which is, I'm going to write out the whole thing. I often write out things instead of writing summation notation because then I can see what's going on. X to the n minus 1 plus dot 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 plus up to a0, this thing, dx, is equal to, well, let's go and find the antiderivative. Conveniently, the antiderivative is an over n plus 1, x to the power n plus 1, plus dot dot dot, plus it goes to a0 times x. And we want to somehow take this whole thing between the limits from 0 to 1. And now you see when you plug in the 0, it's really nice. You plug in the 0 and all of these x's are there, so the whole thing dies. And when you plug in 1's, x to the power anything is just 1. Multiplying by it doesn't do anything. And so this is just equal to an over n plus 1 plus an minus 1 over n plus dot 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 plus up to, it goes to a0. That's convenient. And that's exactly what we had here. That was 0. So this is 0. Any other ideas? Let's see. It looks like we've got more people interested. John Wan.
I was thinking if you could find that the function is positive at some point and then negative at another point, then it has to be a root.
Okay, that's another idea. You're using the fact that the polynomial is continuous. So what you're saying is, if you find that the polynomial is, I'll even write bigger equals 0, because if it's equal to 0, you're already done. But if you can find it's bigger equals 0 somewhere, and less than or equal 0 somewhere, since it's continuous, there exists a root. That is true. Okay, more thoughts. I see that there's more hands up here. I'm going to take Dhruva Naidu.
Well, since we know that integral now equals 0, right, we can say that, I guess it's like the mean value theorem. Or since the average has to be 1 mean equals 1.
Okay, so there's this mean value theorem for integrals. Okay, I didn't think that of somebody going to, I didn't think somebody was going to use that, but we do have this mean value theorem for integrals. Let's review what that is. So what is this mean value theorem for integrals? The mean value theorem for integrals say something like, if you're going to integrate from a to b of f of x dx. Does anyone remember what is this mean value theorem for integrals? Since obviously you had an idea, let's see if someone else can finish this. I'll just go with who raised his hand from here. What's this mean value theorem for integrals? Do we have any new raised hands? Oh, I see a bunch now. I see a bunch. So who is M. Garcia 2? I don't see your whole name, but I see M. Garcia 2.
Yeah, sorry, it's not easy.
It's no problem.
But, so it's, if I remember correctly, it's f of b minus f of a over b minus a.
So f of b minus f of a over b minus a, you're close. There is a b minus a somewhere, okay? So I'll write down what you said. You said something like f of b minus f of a over b minus a. So I think what you're getting at is, I think what you got is you got like the mean value theorem for derivatives, right? If I look at f of b, I think that's actually what you got. So let me put that down. So what you got is not quite this, but what you wrote is MVT for derivatives, right? So MVT for derivatives, what happens is that the total change, this is the total rate of change over b minus a, is equal to some f prime something, but we're about to get a common thing. I'm going to take another hand that's here. We have Nicholas Grill. Nicholas Grill? No?
I was gonna say what the other person said.
You were going to say the MVT for derivatives. No problem, no problem. So let's see another hand. So I see Sher Zoi Jan.
You could do capital F of B minus capital F of A, or capital F of B and F of A is the integral.
Whoa. So I think what you're saying is that there is a mean value theorem. Okay, I think what we're seeing is that we need to quote the mean value theorem for derivatives properly, right? So I just wrote the same thing with capital F's, but what's the mean value theorem for derivatives? I need to put something inside here. There's some details, right? Like, let's see who else is here. Rajiv, your name didn't fill out in the Zoom, but I see Rajiv as part of it, and it starts with G.
Okay, so the mean value theorem for derivatives basically says that there exists some c in the interval AB where the slope is equal to the average.
Yeah, for some c in the interval AB. Right, so we happen to have something here for which that mean value theorem tells you could say that the derivative, well, basically it says that if I went this far over this amount of time, there's some time in the middle when my instantaneous speed was the average speed. That's a fairly reasonable statement. And now we want to drag it over here for mean value theorem for integrals. If you want to do mean value theorem for integrals, why they wrote the capital F's there is you could say, well, if the capital F happens to be the integral from a to x of f of something. Oh, it can't be x because x is inside here. Let's translate this properly. What we could do is we say, let the f of t be integral from a to t of f of little f of x dx, right? Suppose I had that. If I have this going on, now I happen to know that the derivative of capital F is equal to the little f. That's this fundamental theorem of calculus, right? So if I've got this, then if I simply plug these together, what I end up getting is that, let's see. Oh, right. I'm just trying to read off what's going on. The capital F of B minus capital F of A. Just to make life a little bit less confusing, let's take out that A, let's put a 0. All right, 0 is just some neutral number, although A would have worked too. But if I did this for capital F, then capital F of B minus capital F of A is actually just going to be the definite integral from A to B of f of x dx. So your numerator is going to just be, well, that numerator over here. So that numerator, let's use purple since I've got purple over there. So this numerator is this piece, right? And then I divide by b minus a. And that's supposed to be equal to, but the capital F prime is just little f of something, c, for some c in the interval ab. Some c in ab. And so the way I often will write this, if I'm thinking about mean value theorem for integrals, I mean, one way is to write it this way, which is actually, this is the average value. Actually, this is a totally legit way to write it. Let's do it this way. We're going to use this. So this one works because this is just saying that the average value of f from a to b happens to be some value of f in between a and b. Makes sense. And then now when we use our question, when we do our question on this, you found out that this was 0. And you found out this was 0 with b equals to 1 and a equals to 0, so you're done. And that finishes the question. So I'm just wrapping this up because we basically finished it at this point. You use 5 with 3. Well, with everything. With 3 and with 1. Well, I can say with 3. And that implies that there exists a c which is between 0 and 1, so that f of c is equal to this integral from 0 to 1 divided by 1 minus 0, which is just 0. And that finishes the question. So that was this. And it turns out that somehow calculus was useful on this question that was about polynomials. The relationship between calculus and polynomials is actually very rich. And in fact, if you ever try to solve differential equations, oftentimes there's methods that use power series. Or if you do Taylor series, polynomials appear just with infinitely many terms. Actually, I can tell you something. When I went to college, I was taking some placement exams to go and see if I could place out of some classes. And I'd never taken a differential equations class in my life. But I thought I'd take the placement exam anyway. And I just went and used power series to go and solve all of the differential equations. You know, like I didn't know anything about how to solve differential equations. But I did know that you could write down like summation a k x to the k and just like find all these relationships between the coefficients and then guess the answers. And afterwards, the professor told me, well, you technically passed the exam, but you clearly don't know how to solve differential equations at all. So we're not going to pass you out of this class, and it's probably for your own good that you go and learn this thing properly. So the polynomials are very powerful. They can let you solve differential equations even when you have no idea how. Let's keep going. More questions. So the next question's on this sheet. What are we going to do here? Right. I want to go up to the classical result, the first classical result, because it's actually an important thing to know about derivatives and polynomials. There's like a nice expression. There are different nice expressions that you can make for these kinds of polynomials where you multiply together a bunch of terms. So I am writing a factored form of a polynomial, x minus 1 times x minus 2 times x minus 3 squared. And when I do that, it turns out that if I'm going to take the derivative has certain relatively nice forms. Let's try. And when I say let's try, I mean I'm interested in what ideas you guys might be suggesting. So I want to take the derivative of x minus 1, x minus 2, and x minus 3 squared. Anyone have any ideas of how you might approach something like this? Hands up. Okay, I see hands are up. Jason Huang.
I guess you could center it around a different point, say like let y equals x minus 2.
Okay.
Rewrite it in that form.
Okay, and just for fun, I'm going to call it u. I'm going to call it let u equals, okay? Because it's almost like a u substitution, except we're doing derivatives. So if you did this is very clever. What you're saying is that, you know, multiplying 3 of these, actually it's 4 of these binomials together, you get a big mess. But if you do this reordering, then what you have is, then it's the same as x minus 1 is u plus 1. and then you've got a u, and then you have a u minus 1 squared. And then so if I wanted to simplify that, that's actually nice. I see a difference of squares. It's like u times u squared minus 1 times u minus 1. Where what I just did here is I went and said, I have a u plus 1 times a u minus 1. I know that. That's u squared minus 1. And so now it's really nice. It's very simple stuff. It's just going to be two binomials. So it's just going to be u times, what is this? U cubed minus u squared minus u plus 1. Actually, this is kind of elegant. This is u to the power 4 minus u to the power 3 minus u to the power 2 plus u. Now what? Suppose you've done this. What's next? I guess people all expect the answer is like, you just derivative it, right? You just take the derivative of it. On the Wednesday class, I was asking people, is there a better word? Like, what's the right verb for derivatating? Is it is it like what? Deriving? And then somebody pointed out, it's got a word for that. It's called differentiating. So yes, but that's just like, doesn't sound as nice as derivatating. Although I then challenged the person. I was like, hey, that is pretty good. Yes, the verb form of take a derivative is differentiate. But there is a word in math that I have not yet found a good verb form for, and that's the one called taking the determinant of a matrix. Like, what's that? Determinating it. I will say I haven't found a good word for that, but the differentiating, we'll call it this. This is differentiating it. Okay, so we differentiate this thing. Often I just write DER colon. Differentiate it. We get 4u cubed minus 3u squared minus 2u plus 1. And then I guess you substitute the u back in. Okay, you substitute. Oh, I see that people have some ideas. Evaluating. Oh, you're great. You're like, how do you talk about determinating? You just evaluate, right? And you could determine. But anyway, let's finish this. So now what you do, you put in the u, right? So then that's going to be equal to 4 times, what is it? U was x minus 2 cubed minus 3 times x minus 2 squared minus 2 times x minus 2, and then plus 1. And we could say that that's the answer. I will want to warn you of one thing. If you ever do a u substitution, there's one more step you usually have to do to be careful. When you do a derivative where you say, I just go and substitute the u in, I mean, for example, you're not allowed to do this. Watch, I'm going to take the derivative of sine e to the power of cosine of x plus log of x. The way I do this, oh, that's too easy. Plus log of x is too easy. There's an e to the power. Anyway, let's just do cosine of x. If I want to do this, I could just say, hey, u, this is u. So now I'm doing sine u, and the derivative is cosine u, and that's equal to cosine of e to the power cosine x. That's not okay. So this is not okay. Obviously this is not okay, or else calculus class would have been too easy. You just let the most complicated thing be u, and you just do the outside. What do you need to do? I'm just trying to emphasize that because you see you need to do something here, you in theory need to do something here, but it's actually simple. What am I getting at? Raise hand. There's a raised hand. Okay, so Matthew Garcia. Matthew Garcia?
Yeah, we have to multiply times the derivative.
Multiply by the derivative of u, right? Because that's the chain rule. And over here, so this thing is not okay. But when you multiply by the derivative of u, very conveniently the derivative of u is 1. So that's why this is actually the correct answer, even though I'm supposed to multiply by 1. So that's just what I'll say here. Okay, that's one way of doing this question. Actually, it's interesting. Wednesday also came up with this, but somehow this was not what I was intending to do. So there's another thing. Actually, what I was intending to do will give you an answer that's more cumbersome than this, but somehow has some general meaning. So, by the way, I see, let the whole thing be that it's 1. Oh, you're funny. Okay, so that's another way. That would have been a more obvious way to show that this whole thing is dangerous. I like it. Okay, but now I want to say there's another way to do this, right? Another way to get a different expression. This expression you've got here, by the way, is nice. But here's something I would say. If I look at this expression, does anyone know any roots of this expression? I claim there's another way to differentiate this polynomial where you can look at it and say, I see a root. Over here, does anyone see a root of this polynomial? How good's your perception? I see somebody sees 3. You guys are great. I didn't see it when I looked at this. from this I can't see, but 3 is a root. If you plug in 3, what do you get? It's x minus 2 is just 1, so that's easy. So it just becomes 4 minus 3 minus 2 plus 1, which is like 5 minus 5, that's 0. But there's another way to look at this polynomial and I keep saying derivative, but differentiate it to go and get an expression from which you can read off the roots. Let's try another way. So I have x minus 1, x minus 2, x minus 3, whole thing squared. Any other way that I might be able to differentiate this thing? What else could I use? I see that you're raising your hand, Subhashish. It's fine. You got to turn on your mic.
Yeah, sorry. Well, we could use the product rule instead for 4 factors instead of
Okay. So here's an idea. Thank you. I want to use, on this A section, I want to make sure we talk about everything. The purpose of the A section is we're basically using these problems to do like a very fast review of concepts throughout all of math. That's what this is about. And so by using these questions, they give us the something to latch our teeth onto and talk about all these things. So we all know about the product rule. Product rule for derivatives is fg and then derivative is equal to f prime g plus f g prime. There's a reason I always like to write the product rule for derivatives where I prime the f first and then I prime the g. It's because that's a nice way to generalize. If you're ever going to product rule for 3 things, f, g, h, and then prime, this is just equal to, you think of an fg by itself multiplied by an h and then prime. So I'm going to use product rule twice, right? And I'm just going to do this thing quickly. This is equal to, you first prime the fg and then you have an h, plus you leave the fg alone and then you prime the h. Now you have to expand the fg prime and that gives you f prime g plus fg prime h's plus I won't write the parentheses, fg and then h prime. And once you expand the whole thing out, it looks like a nice pattern. That's why I like to say you prime the first one, because you're basically taking turns what you're priming. Plus f, g, h prime. And this thing will work, if you have 4 things multiplied together, 5 things multiplied together. You just take turns priming. So now what you wanted to say is, it's a product rule of 4 things multiplied together. So in that case, what I really have is x minus 1, x minus 2, x minus 3, and then x minus 3. And if I want to do that, I'll write out some complicated polynomial, right? But it's kind of nice. What happens if you prime any one of those terms? What happens if you prime x minus 2? 1. And multiplying by 1 is easy. So actually, if you look at what this whole thing is doing, if you do this to a polynomial in factored form, what you're doing is you're going to add up a bunch of stuff where you take turns deleting one of the factors. That's how I often like to think of it or remember it. So I often think that the derivative is equal to the sum of take turns deleting a factor. There's only one problem. This is not how you write mathematical expressions. That's just not an expression, like take turns deleting a factor. So we want to have another way of writing that. And there's a particularly elegant way, which is what I wanted to make some mention of in this session. Particularly elegant way where you can write this as it's actually equal to the original polynomial but multiplied by something. So I want to write in the square brackets what you might multiply this original polynomial by. It will be a legitimate algebraic expression which symbolizes deleting out a factor each time. Does anyone want to suggest what this might be? I see a raised hand. I want to give as many different people a chance as possible. George, Joe?
You would multiply by the sum of the derivative of the polynomials divided by the polynomial. The FGH would do F prime divided by F.
Oh, that's a good way of doing it. Okay, so you're saying that this thing here, let's just go here, right? You could say this is equal to, it's just the FGH multiplied by F prime over F plus G prime over G plus H prime over H. That is true. And in this particular case, I see there's more people with hands. Is there a simpler way? I see, what is it, Sana Imani?
Yeah, though I actually thought of a similar approach.
Ah, so you're doing
I-
similar.
I-
Okay, no problem. John Wang, is that what I see here? John Wang?
I think the same thing, so you just replace the f prime and g prime and prime with 1.
Yeah. So because the derivatives here happen to be 1, right? So I just have something simple. I saw somebody else also wrote the word reciprocals. It's just 1 over x minus 1, 1 over x minus 2, 1 over x minus 3. Actually, there's 2 of them. So we can write 2 over x minus 3. Now, somebody on the Wednesday class pointed out that what I just wrote down, there's a slight issue of what if x equals 1, 2, or 3? Then it's like, oh no, you can't really divide by 0. But what this is supposed to mean is, it turns out that if you were to expand this whole thing and multiply it out, you're going to get a legit polynomial. So there's something nice. It's not going to give you a weird rational function where there's an asymptote where something is divided by, like 5 divided by 0. It'll only be 0 divided by 0. So this is true for all values of x except 1, 2, and 3. However, it's already very useful. I see that some people are saying things. Oh, fun fact. Zivan Vasquez is saying, fun fact, I think that Feynman popularized this expansion trick. Yes, Feynman did popularize a lot of things. That is also true. And there's a raised hand. Sana Imani?
Yeah, so I'm guessing because, like just from extension of what we've said, because it deletes one factor each time, and there are 2 of the x minus 3s, so there'll always be an x minus 3 factor.
Yes,
So that
okay.
is definitely a root of the polynomial.
Okay, so that's very good. So what you just noticed is you just jumped one more step, which is what we were going to do next, which was, remember I said, hey, if I wrote it this way, why is this any better, right? If I wrote something like this, either the one with the reciprocals, or if I wrote this thing with the words, how is this any more useful for finding out whether there are any roots? And what you just noticed is, well, if I'm going to take turns deleting one of the factors, when I get here, no matter what, there's going to be at least one x minus 3 left in every one of the terms. In fact, when I delete the first factor, there's 2 x minus 3's multiplied together. Delete the second one, there's still 2 x minus 3's multiplied together. When I delete one of the x minus 3's, there's the other one. And when I delete the other one, there's the first one. And so what you've just observed is that this particular polynomial here, this is always going to be x minus 3 times, some legit polynomial. Yeah, I'll just write poly. Some legit polynomial. I'm emphasizing that it's some legit polynomial because, if I'm allowed to say x minus 3 times anything, I could make the other thing be like blah, blah, blah over x minus 3. And that would be bad. I mean, not that would be bad, then I'd be saying too much. But when I emphasize that it's times some polynomial, I mean you really could factor out the x minus 3. Because we've gotten to here, and because we just made this observation, we have just found out that somehow if I've got this polynomial and x minus 3 is squared, then when I take the derivative, x minus 3 is still a root. This is interesting. If you haven't seen this before, I'm curious if you have a hypothesis or a random conjecture about something that might be true in general. Some people may have seen the fact that I'm about to talk about. But if you haven't seen this before, do you want to make a wild guess of something that might happen now that I've said something about like some power and then some root? We're basically discovering an interesting fact about polynomials. So I see there's a raised hand, Rajiv, and all I see is G-O-D-S as the beginning of your last name. Say again. Actually, what's your full name? I'm curious.
God's
Say again.
G-O-D-S-E.
Oh, G-O-D-S-E. Then why did it cut off so many letters? Okay. Okay. G-O-D-S-E. So Rajiv Godse. Yes.
Okay, so I think that if you have a polynomial which has a root with a certain multiplicity, then the derivative will have like that root with the multiplicity times 1.
Okay. Polynomial with root of multiplicity. What should I use? M. M for multiplicity. Implies that the derivative has that root with multiplicity m minus 1. And actually, I'm going to say exact multiplicity. Sometimes people, n minus 1. Sometimes people say like, oh, I have a root of multiplicity 2, and what they mean is at least 2. No, here I mean exactly. So it's a root of multiplicity exactly m, and it has, the derivative has a root of multiplicity exactly n minus 1. This is a very powerful theorem for polynomials, and let's go and prove it. So this is now the next question that we're going to play with, not the question on the sheet, but inspired by the questions on the sheet. How might we want to set up something like this? We're not going to talk about x minus 1 times x minus 2 times x minus 3 squared anymore. We're not going to talk about an explicit polynomial. Instead, I want to prove this statement in general. How might you try to set it up? Okay, Jack. I see Jack Parkhouse has made a comment.
I don't know if this is right, but you could set up an equation starting with x minus n to the m.
Okay, you're going to be like, hey, let's go and put that root in, right? So let's suppose, and I'm going to call the root r instead of n, only because, and there's nothing wrong with what you've said, it's just that I'll give you some of these conventions we often use. N is usually reserved for the degree of the polynomial in polynomial theory, so we'll just save the n for that. But let's suppose r is a root of the polynomial of multiplicity m equal to m. Then it turns out that you can actually always factor your polynomial. In fact, that's what multiplicity even means. We're using something called the fundamental theorem of algebra, which says that every polynomial, you can factor it as x minus all of the roots to the various multiplicities. So this fundamental theorem of algebra gives you that the polynomial is equal to, I'm leaving a space for some reason, I'll write x minus, the first root to the power of the multiplicity of the first root times x minus the second root to the power multiplicity of the second root, and so on up to x minus, let's call it the kth root, multiplicity k. And of course, r is one of these ri's, and then the m is the corresponding mi. Can anyone tell me why I left a space? This is just like a very minor technical detail, but why is there a space there? So, Matthew, coefficient. Oh, we already saw. But Sana, you were saying something.
It's already mentioned in the chat, but it's the leading coefficient.
Yeah, there's a leading coefficient, a, something like this, right? There's always a leading coefficient. It could be 1. Right? But so that's what the fundamental theorem of algebra lets you do, where these roots are actually often, well, they can be complex numbers. But now if you have that, the root is and there's something interesting here. We're talking about the derivative, and I just mentioned the word complex numbers. So here's something that I want to add. You see, usually we learn calculus as real analysis first, right? And of course, in university, we call it real analysis. In high school, we just call it calculus. But in high school, you basically take it as a given that whenever you take derivatives and integrals, you have real functions going in. And here we're about to take a derivative of something where we said that there's a root of some multiplicity, but the roots from the fundamental theorem of algebra could be complex numbers. And it turns out that the theory of taking derivatives of complex polynomials exists. It turns out it's possible for any complex polynomial to define the derivative in a reasonable way, and it turns out that the way you take the derivative is the way you usually do, which is you take the exponent and then you push it down and you take the, you make the exponent minus 1. The entire theory of why this is legitimate is the theory of complex analysis, which is a really interesting class, and I hope that at some point when you're at CMU, if you decide to be a math major, you'll take that class. And that's basically telling you that you can take derivatives of complex polynomials. But you can't actually take derivatives of all complex functions. There's something special, and this is the notion of what's called complex differentiability. But that's a more advanced course. But anyway, back to here. It's like, okay, suppose I wrote this thing, fundamental theorem of algebra tells me this, and now I need to show that somehow the roots have the multiplicity minus 1. You know what? I'm going to change up what you said a little bit. I'll say R1 and M1. And why I did that is because as long as we do it for the first one, then you're good for all of them. So what can I do next? So now we've set up the whole thing, we've factored the whole thing, and now we want to say something about the derivative. Any ideas? Hands up. I see a hand is up. So we have Adavit, Nini.
You can just take the derivative using that nice identity that we just figured out.
Okay, let's take the derivative. And that nice identity is going to tell me, let's do the one, I assume when you say nice identity, you mean the one where I wrote in English of like take turns, yeah.
Exactly.
Yep.
So like you would write it as the original polynomial
Yep.
each multiplicity over each factor.
Oh, okay, we can do that way too. Okay, the original polynomial times, and it's nice. Okay, we use this one. Multiplicity over each of the factors. Plus plus mk over x minus rk. Where we understand this to mean that, if you multiplied it all out, you would get a legitimate polynomial. We're not going to have any dividing by zeros. So now if I look at this, what's the deal with the x minus r1? Well, you see, if you tried to multiply this out, what would you end up getting? Well, the polynomial here, I think you're saying to do this step, what you're thinking about is you have your a, and you have your x minus r1 to the power m1, and then you have like other stuff, but these are roots. I'll write polynomial. Well, you know what? Let's write the whole thing. Times ... times x minus rk to the mk, and then we have this square bracket, m1 over x minus r1, plus the important thing is the other things are not divided by x minus r1. m2, oh, I know. I'll write m not 1 divided by x minus r not 1. This is not the right way to write mathematics notation, but I think it maybe communicates the meaning faster for the purpose of this class. But once you write this out and you multiply it together, what do you get? Your first term is going to give you something which has x minus r1 to the power m1 minus 1. So I took 1 away because I had to divide by x minus r1, times a bunch of stuff. I have an a. I have a bunch of things which are x minus r not 1s to some stuff, to some funny powers. Right? This is not really just one thing to a power. It's like many of them multiplied together, but I'm emphasizing that there's no r1, no x minus r1 there. That's the first thing. And the second thing is going to give you x minus r1 to the power m1, legitimately m1, times a, and then times a bunch of other things. So this thing is another polynomial. I'm trying to think if that's the best way. Yeah, I think that's the best way to write this thing. Polynomial in x. So I want to digest what I've said. Oh, I see that there's idea and also raise hand. I want to make sure we got some of those. So just a second. Did I get your idea yet, Rasid Tanvir?
Sorry, that was before.
Oh, that was before. Okay, sorry about that. Okay, so those are from before. So both of those might have been from before. But what I want to emphasize is what we just did here is we pulled out something where if I actually expanded the whole thing out, my first term of stuff multiplied together would have a power m1 minus 1, and then some stuff multiplied by it, which is already in factored form, but all those factors happen to not involve x minus r1. And then I add to that, all the other terms have a factor of x minus r1 to the m1, and since all the other terms have that factor in it, I'll just go collect them all into some polynomial, legitimate polynomial. Can anyone tell me why I bothered to be this careful? In some sense, I could have looked at this, and I'm sure many of you said, well, look, it's got a power of x minus 1 to the m1 minus 1, for sure, because I'm only going to knock away one of them. So that's telling me that there will be a factor of x minus r1 to the m1 minus 1 for sure. But why do I need this extra work? Raise hand. There's a... yes, Sana Imani?
Yeah, I mean, if the other terms that you had, which in this case is x minus r1 to the power m1, that if it was lesser than m1 minus 1, you wouldn't be able to factor it out.
Okay, that's true. So it's true that if on this one I've got the power m1 minus 1, but over here I got the power like 2, which is suppose that was smaller, then I wouldn't be able to factor out. That is one issue. But there's another issue also. So I need two issues. So the first one is it's bigger power. Great. Since it's bigger power, I can factor out the m1 minus 1 power. But there's another issue at hand. And Rajiv?
Yeah. So when you showed that the other on the left term that you're multiplying by x minus r to like not 1, you show that the multiplicity is basically exactly m1 minus 1 and not greater than that.
So this has no more x minus r1, very important. And how about this stuff?
Yeah, and over there you showed that there was at least m1.
Got it. So when I do this, I think what we're getting at, we're seeing that what we're getting at is I needed to show that there's no factor of x minus r1 to the m, right? Because you see, I have on the right side here multiplicity equals m minus 1, not at least m minus 1. And so far what I've written down here, you could look at it and you say it's at least n minus 1. That's good. But how do I know it's not more? And the way you know it's not more is you look at this and you say, well, this guy is not multiplied by any more, and this guy is more. There's a way to tie this up very tightly. Let me just see if there's somebody who wants to add a comment here. Adavid, Nini?
I was going to say, once you factor out n minus 1 of the x minus
Aha.
r1, you're left with something that's not divisible by x minus r1 plus something that is divisible by x minus r1. So the entire result is not divisible by x minus r1.
Good. So it's a poly not divisible by x minus r1 plus x minus r1 times a poly. And this is just like what you think about when you think about like normal integers. If I have a not multiple of 5 plus a multiple of 5, it's not a multiple of 5. However, if I took a not multiple of 5 and I plus a not multiple of 5, you could get lucky and get a multiple of 5. Does that make sense? I'm emphasizing this little detail here of I'm saying that, hey, one of them is a multiple of 5, and the other one is, one of them is a multiple of x minus r1, and the other one's not. And because of that situation, then sum them together, and it won't be a multiple of x minus r1. So that's the detail here. And in fact, what you've also seen is we've just started talking about polynomials as if we're factorizing them. And when you take an abstract algebra class here at CMU, whether it be algebraic structures or whether it be math studies algebra, you would, or maybe you already did, but you'll see that polynomials have certain properties that are quite similar to these kinds of numbers, whole numbers that you're dividing. And you'll learn about things like unique factorization domains and so on. But anyway, that's what's going on here, and that's why I know that over here I don't have any more factors of x minus r1. And so that finishes the proof. Okay. Any questions, by the way? This is a very powerful theorem. Maybe I want to use this as like the place I tie up this particular class. This is a really powerful and very important theorem that somehow got polynomial. When you differentiate it, the multiplicities kind of retain, except they lose 1. Maybe let's like dig a little bit into this. What's the implication of this if the multiplicity is 1? Let's just like play with this a bit, just to digest this theorem, right? Suppose I have a polynomial and it has a root with multiplicity 1. What does that tell me about the derivative? Jack Parkhouse?
Sorry.
Oh.
I thought, does it imply that it can't be a root?
Yeah. So you see what I'm trying to say? The value of getting this equals is that we would get equals 0. Whereas if before we had just satisfied ourselves with saying bigger equals 0 doesn't tell you anything. I guess we've also just now talked about then what's this convention we want to use for the purpose of today's class of what's a root of multiplicity 0. Well, it's not a root. But I don't want to just say that's a definition. If you look at the way we did this whole proof, if we did this whole proof and you had that m equals 1, then when you drive all the way down to here, you get something to the power 0. That's just a constant. That's just a number. It's actually 1. Nothing there. Plus a polynomial which is not divisible by x minus r1, plus x minus r1 times a polynomial. So when you look at the whole thing, then x minus r1 is not a factor, and it's in fact not a root. So what we have just found out is a neat fact, that if you take a polynomial, anywhere that there's a root with no multiplicity, then the derivative doesn't have that as a root. But maybe to close the class, let me say, that's also what you've seen if you ever draw graphs, right? So, this is something I guess I noticed when I was taking calculus at high school at some point. It's like if you go and draw a graph, and if this happens to be the graph that you see, then over here, it's pretty obvious that the derivative is not 0. And that's because you see the graph is going right through, and the slope is not 0, right? So when I have here, it's not a root, right? I have that the polynomial is going through, it has exactly one root, and the derivative is not going to have a root here, because the derivative here is like some positive thing. But something that was always neat to me was when you look at something like this, it's like, well, yes, it's got a multiple root in the normal sense, and it also happens to have a root of the derivative because the graph is itself at a local extremum. And so this is all kind of consistent. Okay, well, unfortunately, that's all the time we've got today. Thanks to everyone for joining today's Putnam class. Hopefully this was an interesting foray into calculus meets polynomials. And we'll get back together again next week. As usual, just like try to do 2 of the questions. Try to do 2 of the questions. Spend 2 hours is all we care about. And please work with other people, because it's much more fun that way. So I'll see you next class. Sure.